puzzle in fundamental physics. How do we square general relativity with quantum mechanics? You've got G.R. Einstein's masterpiece, right? Describing planets, stars, gravity as curved spacetime, all smooth, continuous. And then you have quantum mechanics, the microworld, atoms, particles. It's all probabilities, discrete jumps, and just weirdness.
Cool.
And maybe the peak of that weirdness, something Einstein himself dubbed spooky action at a distance, quantum entanglement. He, Podolsky, and Rosen pointed this out way back in 1935. The idea is, two particles can be linked so deeply that measuring one instantly affects the other, no matter how far apart they are, miles, light years, doesn't matter, which seems to just fly in the face of locality, right? The idea that nothing travels faster than light.
Exactly. And that's the setup for today's deep dive. How does string theory, maybe our best bet for a theory of quantum gravity, offer a really radical way of looking at this spookiness? It's not trying to get rid of it. It's trying to explain it. By suggesting space-time itself isn't fundamental, the claim, and it's a big one, is that space-time is emergent, kind of sewn together by entanglement itself. That's what we want to unpack.
Okay, wow. Space-time built from entanglement. That's a lot.
Yeah.
So before we dive into string theory's take, let's really get a handle on entanglement, because this isn't just, some philosophical thought experiment anymore. It's real. It's confirmed. And it started with Einstein trying to poke holes in quantum theory with the EPR paradox. So picture this. Two particles, A and B, shoot off from some source. Let's say they have zero total momentum. So if A has momentum x, B must have momentum mass x. Simple enough. Now, Alice, our observer, she can choose. Measure particle A's position. Because they're linked, she instantly knows B's position. Perfectly. Without touching B. So EPR said, okay, if you can predict something with certainty without disturbing it, it must be real, an element of reality. So B must have a definite position all along. But Alice could also measure A's momentum. Same logic. She'd instantly know B's momentum. So B must also have a definite momentum. And there's the rub. Quantum mechanics, Heisenberg's uncertainty principle, says, nope, you cannot know both position and momentum precisely at the same time. So EPR concluded quantum mechanics was incomplete. There must be some hidden information, hidden variables predetermining these things, saving locality and realism.
Which naturally leads to the question. Okay, interesting thought experiment, but how do you actually test that? Is it just philosophy or is it science? And that's where John Stuart Bell stepped in, 1964. Bell's theorem was, well, a total game changer. He basically translated that philosophical argument into cold, hard math, a testable prediction. He figured out how to test any theory based on locality and realism, these hidden variable ideas. He used examples like entangled electron spins. If one spin up, the others instantly spin down, right? Perfect anti-correlation. Bell derived an inequality, basically a mathematical limit. If locality and realism hold, the correlations between measurements at different angles must stay below this limit. Quantum mechanics, though, predicted that for certain setups, this inequality would be broken, violated.
Okay, so the gauntlet was thrown down. What actually happened when they ran the experiments? Did Einstein win, or did quantum mechanics? Well, starting with a lane aspect in the 80s, and then loads of more precise tests since. The results are just overwhelming. Nature consistently, decisively violates Bell's inequality. It follows the quantum predictions perfectly.
Which forces a really uncomfortable choice on us. We have to ditch either realism, the idea that particles have definite properties before we measure them, or locality, the idea that influences can't travel faster than light. Standard quantum mechanics basically throws realism under the bus. It accepts this non-local probabilistic reality. But, and this is absolutely crucial, you have to remember the no signaling principle. Even though measuring particle A instantly collapses particle B's state, you can't use this to send a message faster than light. Alice's result, random. Bob's result, also random. It's only when they get together later, maybe call each other, that they see the correlation. So instant correlation, yes. Instant communication, no. So the bottom line is whatever deeper theory comes along, it can't just wish away this non-local weirdness. It's baked into reality.
Right. So this non-local quantum weirdness is here to stay. How on earth do we match that with gravity? Which brings us, finally, to string theory. String theory's foundation is, well, pretty out there. It says fundamental particles aren't points. They're tiny, one-dimensional vibrating filaments. Strings, when I say tiny, I mean unimaginably tiny, like Planck-length tiny, 10 to the minus 35 meters, way, way smaller than anything we can probe. But the elegance is, like a violin string playing different notes, different ways these strings vibrate correspond to different particles. An electron is one vibration mode, a photon another, a quark another. It's a path towards unification.
And what's really kind of amazing is how gravity just naturally falls out of this picture. It turns out that one specific way a closed string, one forming a loop, can vibrate It has exactly the properties of the graviton,
Yeah.
the hypothetical quantum particle that carries the gravitational force. So string theory doesn't just allow for quantum gravity, it actually predicts it, requires it almost. And this also solves a huge problem with trying to quantize gravity using point particles, which leads to these uncontrollable infinities in calculations. Strings sort of smear out the interaction, taming those infinities. It just works mathematically.
Gravity included automatically. That's huge. But didn't you say it comes with baggage? Like
Yeah.
extra dimensions? Where are they?
Exactly. Turns out string theory needs more dimensions to be mathematically consistent, typically 10 or 11 space-time dimensions, not the 4 we experience.
Yeah.
The standard explanation is compactification. The idea is these extra dimensions are curled up really, really small. Think of a garden hose. From far away, it looks one-dimensional, like a line. Get close, you see it has a little circular dimension, its thickness.
So these extra dimensions are supposedly trolled up into complex shapes, like Calabi-Yau manifolds, way too small for us to see. Though this leads to the landscape problem, because there seem to be gazillions of ways to curl them up, meaning maybe gazillions of possible universes. Makes predictions hard.
Yeah, that's definitely a challenge. And we also need to quickly mention branes and supersymmetry, or CSY. Branes are basically higher dimensional surfaces or membranes that strings can end on or move along. In some brane world ideas, maybe our whole universe is a three-dimensional brane floating in a higher dimensional space, the bulk. Our particles might be stuck on the brane, but gravity, being related to closed strings, could leak out into the bulk. That could explain why gravity seems so weak. And then there's CUZY, supersymmetry. It's this proposed symmetry between matter, particles, fermions, and force carriers, bosons. Every particle would have a heavier superpartner. It helps stabilize the theory. Mathematically, it's very elegant. But the big problem is we haven't found any evidence for these superpartners. Years of searching at the LHC, nothing yet.
Okay, so strings, extra dimensions, maybe branes in AESY. It's a complex picture. How does this whole framework connect back to entanglement and this emergent space-time idea? Is this where holography comes in?
Precisely. This is where things get really wild with the holographic principle. And its roots are actually in black holes. Back in the 70s, Wittgenstein and Hawking discovered black holes have entropy, which is basically a measure of information. But the super weird part was the entropy wasn't proportional to the black hole's volume like you'd expect. It was proportional to the surface area of its event horizon.
Wait, the information is on the surface, not inside. That feels wrong. Like a library storing books only on its walls, not filling the room.
Exactly. Totally counterintuitive. And this led Cheethooft and Susskind to propose the holographic principle. Maybe all the information in a volume of space is something encoded on its boundary, like a 2D hologram projection creating a 3D image. The universe itself fundamentally might be a hologram.
That's a cool idea, but it sounds very conceptual. Did it ever become more concrete? It sure did. In 1997, Juan Maldacena came up with the AD-S-CFT correspondence. This was massive. The second superstring revolution, some call it. It's a duality, an exact mathematical equivalence between two totally different looking theories. On one side, the bulk. That's quantum gravity, like string theory, living in a specific curved space called anti-de Sitter space, or AD-S, higher dimensional. On the other side, the boundary. That's a conformal field theory, or CFT. It's a quantum theory without gravity, living on the lower dimensional edge, the boundary of that AD-S space.
And it's incredibly powerful. Often when calculations are impossible on one side, they become straightforward on the other. It's like a dictionary between gravity and quantum field theory.
Okay, a dictionary. But how does that dictionary translate entanglement into geometry?
They came a bit later, in 2006, with Ryu and Takayanagi. They found the specific entry in the dictionary, the Ryu-Takayanagi formula. It says that the entanglement entropy, a measure of how entangled a region on the boundary CFT is with its surroundings, is directly proportional to the area of a specific minimal surface in the bulk ADS space that ends on that region's edge. So boom, a purely quantum information thing, entanglement, equals a purely geometric thing area.
Wow, so entanglement isn't just happening in space, it's somehow related to the amount of space, or at least area.
It's even deeper than that. The implication is staggering.
Yeah.
The geometry of the bulk spacetime isn't fundamental. It emerges from the entanglement structure of the boundary theory, Mark van Ramsdonk put it dramatically. If you could magically decrease the entanglement on the boundary, the bulk spacetime would literally start to pinch off and fall apart.
So space is like woven from entanglement threads. If you cut the threads, space dissolves.
That's the essence of it. Entanglement isn't just in space-time. Entanglement creates space-time. It's the quantum glue holding space together.
Okay, my mind is officially blown, and this leads us to the grand finale of these ideas. ER equal EPR. Right.
Yeah.
Proposed by Susskind and Maldacena in 2013. Just 3 letters equal 3 letters. ER equals EPR. ER stands for Einstein-Rosen bridge. That's the technical term for a wormhole, a shortcut through spacetime. And EPR, as we know, is Einstein-Podolsky-Rosen, shorthand for quantum entanglement.
So the conjecture is breathtakingly simple to state. Wormholes are entanglement, that spooky option at a distance. It is a geometric connection, a wormhole, linking the entangled particles. The non-local quantum correlation is actually a non-local piece of spacetime geometry.
Whoa, so instead of some mysterious influence, it's an actual, albeit tiny, tunnel through space connecting them. But wait, can you send signals through these wormholes? Because that would violate the no signaling rule.
Excellent question. And the answer is crucial. No. The Einstein-Rosen bridges, relevant here, are the non-traversable kind. They pinch off too quickly for anything, even light, to pass through from one mouth to the other. And this non-traversability beautifully mirrors the no-signaling principle in quantum mechanics. You have the connection, the correlation, but you can't use it to send a message. The geometry forbids it.
Okay, that fits neatly. Where did they even get this idea? Was it just plucked from thin air?
Not quite. It grew out of studying a specific setup in ADS-CFT, the eternal ADS black hole. This describes 2 black holes existing forever, connected by a non-traversable wormhole through their interiors. And in the holographic dictionary, this geometric setup in the bulk corresponds exactly to 2 CFTs on the boundary that are maximally entangled with each other, in a special state called the thermal field double. So EPR basically takes that specific example and says, okay, maybe this isn't just about black holes. Maybe it's universal. Maybe any pair of entangled particles, like 2 electrons spun off from the same decay, are connected by a tiny quantum wormhole. Of course, these wouldn't be smooth classical wormholes, but some kind of fuzzy, quantum gravitational, perhaps stringy connection at the Planck scale. And there's even been some recent theoretical work, late 2024, by Xinjiang and others, claiming to actually derive the wormhole geometry directly from entanglement calculations in certain CFTs. So it's gaining some mathematical traction. But let's be super clear. This is not sneaking hidden variables back in. It fully embraces quantum mechanics. The wormhole is the entanglement. It's not a channel for hidden signals. It's a geometric picture of entanglement within quantum gravity.
Okay, a geometric picture. The real test, though, is can it solve problems? And there's a massive one it might address. The black hole information paradox, or even worse, the firewall paradox, right? The information GR says information falling into a black hole is gone forever. Quantum mechanics says information cannot be destroyed. Total conflict. Hawking radiations seem to make it worse, suggesting black holes evaporate, taking the information with them.
And then ANPS Almhiri, Meroff, Polchinski, Sully came along in 2012 and sharpened the paradox into the firewall paradox. They showed a clash between 3 core principles we thought were solid. 1, unitarity information isn't lost. So outgoing Hawking radiation, call it B, has to be entangled with all the radiation that left earlier, call it C. 2, the equivalence principle falling into a black hole should be uneventful at the horizon. Smooth sailing, no drama. 3, locality standard quantum field theory works outside the singularity. The problem: particle B is also created entangled with a particle A that falls into the black hole. But quantum mechanics has this rule, monogamy of entanglement. Particle B cannot be fully entangled with 2 separate things, A and C, at the same time. So if unitarity holds, B entangled with C, its entanglement with A must break violently at the horizon. This break releases huge energy, creating a deadly firewall, which kills the equivalence principle.
Ouch. So either information is lost or space-time rips apart at the horizon in a fiery wall. Nasty choice. How does ER EPR get us out of this mess?
It offers a really elegant way out by challenging a hidden assumption that A, the inside particle, and C, the old radiation, are truly independent systems. ER EPR, combined with holography, suggests the black hole interior, where A is actually built from or encoded in the Hawking radiation C that has already escaped. So the entanglement BA is one wormhole. The entanglement BC is another set of wormholes. But crucially, A and C aren't separate. They're different ways of describing the same underlying quantum degrees of freedom connected through the wormhole geometry. So B isn't trying to be entangled with 2 different things. It's entangled with one complex system that has both an interior A and exterior C description. Monogamy isn't violated. The firewall just dissolves because the things it was supposed to separate were connected all along by wormholes? Essentially, yes. No broken entanglement, no firewall. smooth horizon preserved. The paradox evaporates because the geometry is the entanglement.
That is her. Incredibly neat. Almost too neat. Okay. Critical hats on. This all sounds amazing, but what are the actual problems? Starting with string theory itself. Well, yeah, there's the elephant in the room. That's
Yes.
not even wrong criticism of string theory. It famously doesn't make easily testable predictions. Instead, it has this enormous landscape of possible solutions, maybe 10 to the 500 or more possible universes. It's hard to prove wrong if it can fit almost anything, and tied to that is the lack of any direct experimental evidence. Decades of searching for supersymmetry, for extra dimensions, nothing's turned up. It remains this beautiful mathematical structure, but is it physics?
Absolutely. And ER EPR, specifically, has its own set of deep conceptual and technical issues. One big one is potential conflict with quantum linearity. Quantum mechanics says if you have state 1, no wormhole, and state 2, no wormhole, their superposition is just a mix. How does a superposition of no wormhole states become a state with a wormhole? That's not obvious how that works. There's also the question of genericity. Does ER EPR apply to any entangled state, or just the very special, highly symmetric, maximally entangled ones where the math works out nicely, like the TFD state giving a smooth wormhole? What about messy partial entanglement? And, as we touched on, the whole thing relies heavily on as CFT, but our universe is expanding. It looks like de Sitter, DS space, not anti-de Sitter, EDS. Making that holographic dictionary work precisely for DS space is a huge unsolved challenge. So does this beautiful added story even apply to us?
So we have conjectures built on a theory that itself lacks direct proof. It's elegant, but it feels like a house of cards, maybe. If these connections, these wormholes, are real, they must have some physical effect, right? Even if tiny. What happens when we try to calculate those?
This is where things go from speculative to, well, potentially disastrous for the simple ER EPR picture. Direct detection is impossible. They're Planck scale. But indirect effects, people have tried to estimate them, and the results are not good. Let's look at 3 attempts. 1, the energy of entanglement. Based on the geometry, a maximally entangled pair, like positronium, electron-positron, should have a wormhole connecting them with an energy equivalent to about 127 electron volts. A tiny mass, but huge energy. This extra energy should show up when they annihilate. But experiments measure the annihilation energy very precisely. It matches the rest mass energy with maybe a few thousand eV uncertainty. The prediction is off by 21 orders of magnitude. It's colossally wrong.
21. Okay. What else?
2, speed of entangled photons. If an entangled photon is dragging a wormhole with that much mass energy, it should travel slower than c. We know the speed of light is constant to incredible precision, about 3.5 parts per billion. This limits any extra wormhole mass effect to less than 10 to 5 eV. Compare that to the 1027 eV predicted by the first calculation.
Yeah.
These 2 predictions from the same idea are off from each other by 32 orders of magnitude, and both are wildly off from observation.
It's not just wrong, it's inconsistent with itself. Yikes. Is there a third strike?
3rd, weight of entangled systems. If entanglement adds mass via wormholes, a big collection of entangled particles should weigh more. Calculations suggest, say, 109 entangled electron pairs in liquid helium should weigh kilograms more than expected.
Yeah.
Needless to say, no experiment in condensed matter physics has ever seen anything remotely like that. It would be glaringly obvious.
So just catastrophic failures when you try to calculate actual physical consequences. How do proponents even respond to discrepancies that large?
Well, the main defense is often characterized as a kind of retreat to non-falsifiability. The argument goes, but these are highly quantum objects at the Planck scale. You can't just apply classical concepts like mass and energy in this naive way. The real calculation requires a full theory of quantum gravity, which we don't have, which might be true, but it also conveniently shields the idea from being ruled out by these calculations. It pushes verification or falsification off into the indefinite future.
So where does that leave us, this idea, space-time woven from entanglement? It's undeniably profound, ambitious, imaginative, a real testament to the human drive to understand.
It absolutely is. It offers this glimpse of a truly unified reality where quantum spookiness becomes geometry, where black hole paradoxes might just melt away. It connects things in such a deep way.
It's a beautiful story, almost poetic, and it's a huge but. It's profoundly unproven. As we've seen, it rests on layers of speculation, faces deep theoretical questions, and seems to crash spectacularly against experimental reality when pushed for numbers.
Yeah. Until there's a clear path to testing it, or these massive challenges are overcome, it has to remain what it is. A magnificent, inspiring, but ultimately speculative vision. A beautiful mathematical dream still waiting for its wake-up call from reality.
So as you finish listening and go about your day, maybe look around. Consider the space you're in, the connections between things. Could it all somehow be secretly stitched together by those invisible quantum threads of entanglement? It's certainly something to think about.